Ladies and gentlemen, this RedGamer.com video, we're going to start a first part of a series of videos discussing a rather large interview with the architects of the Xbox One. Now, this interview is very long, so it's probably going to have to be over a series of videos, but of course as I'm going to be doing explaining of what they're actually referring to, and of course I'll also be doing a lot of analysis as well. So, for the most part I'm going to try and talk in a certain order because the interview's a little bit itsy-bitsy, but what I will try to do is at least speak about virtualization first. Virtualization is fairly simple. The idea is that you're running multiple operating systems underneath one banner, under one piece of hardware. So in other words, to put it simply, let's imagine you have Windows, then you could under your Linux, you could also run Linux, and you could run, say, another version of Windows on your main version of Windows, which is known as host and client. Obviously, the main OS would be the host. So I have done a video on virtual operating systems and stuff, so you can check that out if you're more curious. Anyway, the question was asked of, you're running multiple operating systems in a single box using a single processor. Was that one of the significant changes in designing the silicon? Now, Nick Baker, who is the manager at the hardware architecture team, started out and he said there was a lot of bitty stuff to do. We had to make sure that the whole system was capable of virtualization, making sure everything had page tables, the I/O had everything associated with them, virtualized interrupts. It's a case of making sure that IP we integrated into the chips played within the system, Andrew. And he then of course palmed it off to Andrew Goosen, who is one of Microsoft's chief technical fellows. He began, like Nick said, there's a bunch of engineering that had to be done around the hardware, but the software also was a key aspect in the virtualization. We had a number of requirements on the software side. We can go back to the hardware. From the beginning, the virtualization concept drove an awful lot of our design. We knew from the beginning that what we did want was to have the notion of this rich environment where we could be constantly running concurrently with the title. It's very important to us, based on what we learned with the Xbox 360, that when we go and construct this system, that we don't want to disturb the title, the game, as least bit possible. And so to give a varnished experience on the game side as possible, but also to innovate on either side of that virtual machine boundary. We could do things like update the operating system on the system side of things, while retaining very good compatibility with the portion running the titles, as we're not breaking back compat with titles because the titles are their own entire operating system. By the way, guys, I will explain all this, I promise. I just want to get the main thing done. It's fairly long and lengthy, as I said. But because the titles are their own entire operating systems that ship the game, conversely, it also allows us to innovate, to have great extent on the title side as well. With the architectures from SDK to SDK release, as an example, we can completely rewrite our operating systems memory manager for both CPU and GPU, which is not something you can do without virtualization. It drove a number of key areas. Nick talked about page tables. Some of the new things we have done, the GPU does have 2 layers in page tables for virtualization. I think this is actually the first big consumer application of a GPU that's running virtualized. We wanted virtualization to have that isolation, that performance, but we could not go and impact performance on the title. We constructed virtualization in such a way that it doesn't have any overhead cost on the graphics other than interrupts. We've contrived to do everything we can to avoid interrupts. We only do 2 per frame. We had to make significant changes to the hardware and software to accomplish this. We have hardware overlays where we can give 2 layers to the title, 1 layer to the system and 1 to the title, can render completely asynchronously and have them presented completely asynchronously to what's going on system side. System side is all integrated with the Windows Desktop Manager, but the title can be updated even if there's a glitch, like the scheduler on the Windows side going slower We did an awful lot of work on the virtualization aspect to drive that, and you'll also find that running multiple operating systems drove a lot of our other systems. We knew we wanted to be 8 gigabytes, and that drove a lot of the design around the memory system as well. Okay, so end quote, and let's actually analyze this a little bit, because I realize that some of you may be getting a little bit lost on that. So all virtualization simply means, of course, is that you're creating a virtual operating system. So that's fairly simple. And what they're basically discussing here is almost a GPU pass-through technology. This pretty much allows the virtual machine, or the virtual machine, to access whatever the dedicated GPU's resources are. For example, NVIDIA actually do this using what is known as the grid technology. That's known, or the NVIDIA GPU pass-through technology lets you create virtual workstations that gives your user all of the benefits of a dedicated processor on their desktop. So I'm not sure if you're aware of this, but NVIDIA are one of the big players when it comes to basically providing GPUs, and we know about, of course, SIMD architectures and all of that stuff. We've discussed this quite heavily before. If not, you can take a look under the Xbox One versus PlayStation 4 video, which is on the front page of the channel, and you could have a look at compute architectures. But basically, NVIDIA allow you to do a lot of the compute stuff. So obviously that would be rendering or 2D or video work or video effects, that type of thing. So now that you understand that, let's address another little issue. So one of them was that they were talking about that you can actually update the operating systems on the system side and retain great compatibility with the rest of the titles. Now, to Microsoft, this was very important because, as I'm sure some of you are most likely aware, Microsoft are going to be focused very heavily on apps such as Twitch and whatever else. And they're not running on the main OS, right? They're not running on the game OS anyway, let's put it that way. So you could almost consider it like a single parent, and one kid runs the games and the other kid runs the applications and so on. Now, this allows you to, as Microsoft basically are pointing out, you could do whatever the hell you want with the. Let's just call them. Let's ignore the main orchestrator operating system, and let's talk about the other two. So let's call the first one. Let's just call it 1, the games OS, and let's say 2 is the app OS, just to simplify the verbiage for you guys. So all they're basically saying is, look, you can do whatever the hell you want with the second one. It doesn't matter. The benefit is that you can literally do anything you like. You can delete the file structure, you could format that virtual hard drive, you could have it so that, you put in there the piece of code saying hello world a billion times. It literally doesn't matter. It will do whatever it can with the resources it's got. And this is very important because Microsoft had previously pointed this out, but I'm going to reuse it because it's pretty good. If you have a piece of memory that's earmarked for a game, let's assume, for example, you develop a title, and let's say that it uses, let's say it uses 5 gigs of RAM, exactly 5. But let's assume that Microsoft do an update, and that update to the operating system means that the game has, let's say, 2 bytes, not kilobytes, bytes, less data available to it. You'll actually probably crash the game if you try to run your title that you've developed and spent all that time working on. Why? Because it's quite literally trying to address something that's not there. If you're not too familiar with programming, this is actually pretty simple, but if you're not familiar with it, it can be quite daunting to understand. But the verbiage of programming, most of it is that you're basically, I really need to do videos on this, and I will do them, I promise you guys. I've just been really behind because of the amount of console stuff that I've been covering, but I will do them. The basic premise is that you store data in print. Well, let's just use the word memory containers. So in other words, you're saying this value, this piece of data, is hosted on this memory container here. So it's almost like putting, like, I don't know, envelopes into mailboxes. Just think of like every memory address as a mailbox, and you're storing something in there. Now, imagine if you're going down the road. Let's say there's 500 houses on your road, and let's say you're the postman, and you've got to deliver to 500. So number 500, you're holding it in your hand, and you need to deliver to it. Well, the house has been demolished. Right? Since your last paper round, since your last delivery round, the house has suddenly disappeared. It's, there's just a crater there. So you can't deliver that because it's no longer there. So what happens? Well, you're screwed. You can't deliver that letter. But let's assume that your boss has said, well, you can't come home until you deliver that letter, and we're watching you. In other words, it's monitoring what you're doing. In this case, memory is basically allocated to a resource. If a game needs that, if the game has already been predefined to utilize those resources, it's screwed. So that's why Microsoft are going the virtualization route. Their plan is that, okay, we're going to make it so that the apps can do whatever the hell they want with the memory they're given. Right? You could have an application that, puts bunnies on screen. It doesn't matter. That bunny will not interfere with the game. It's actually a fairly interesting idea. It does have some issues. For example, we know that there are problems, and we'll discuss these later on as the interview progresses, but there are problems with it, including that it takes up more resources, more memory. It takes up more GPU resources as well. Obviously, the Microsoft have said that it's about 10% of the Xbox One's GPU is being used simply for this purpose. I actually quite like the idea in theory. I'm someone that absolutely loves virtual machines and all of that fun stuff, and I think it's quite nice. It could bite them in the butt, however. This is another point, that it's going to be very interesting in terms of updating. I have a feeling that updating this machine is going to be very complicated, but for the game perspective, it's not going to make too much of a difference. Obviously, the app OS anyway, the main OS and the game OS, however, are two different things entirely. They're two different beasts. As far as my understanding goes, the main OS, or the host, if you will, is actually fairly light. In other words, it doesn't actually do that much other than just run the other two. So it's pretty much saying, okay, well, I'm going to do very little work. I'm just going to boss you two around all day. So that brings us to the memory. So he was discussing memory and 8 gigs. Andrew said that it was a pretty early on decision that we made. We were going to have the kind of experience we want to run concurrently with the title, and how much memory we would need. That was one of the really early decisions for them. There have been actually a series of leaked documents out of Quote, which have stated that Microsoft knew they needed DDR3 8 gigs. And the reason they knew they wanted the 8 gigs, the DDR3, is because they knew categorically they required 8 gigs. In other words, 4 gigs of GDDR5 RAM was not on the cards. They couldn't do it with their vision, with their ideas, with the virtual machine and everything like that. All of those things require resources, and so they wanted the snap-in interface and so on. Obviously, some people don't like it, some people do, blah blah blah. But I think it's kind of cool actually. But they knew they needed this memory. And so they decided very early on that 8 gigs was going to be a prerequisite for their machine. And so obviously the 8 gigs, and we're going to discuss this further down, isn't really... It's doing quite a bit of stuff. It is actually handling, for example, texturing and so on. So we'll discuss that a little bit later on. But suffice to say, 8 gigs of DDR3 was... obvious. They couldn't go with GDDR5 because they just didn't think it was going to be abundant enough. They didn't think that the memory modules were going to be large enough, and so on. And so they were pretty much forced down this road. We can argue all day about it, and I've made my opinions quite clear. I still prefer the layout of the GDDR5 of the PlayStation 4, but there you have it. But we'll go into that more later anyway, as I've said. So let's discuss the CPU side. Now, the Jaguar processor, of course, as I'm sure regular viewers know by now, is an 8 cores, and each one handles one hardware thread. Basically running in 2 clusters or 2 modules. Each module has 4 cores, obviously, so 2 times 4 is, 8. So we've gone into like algebra level maths there. Each has each of the cores, each of the modules, let me get the words out, it would help, has its own level 2 cache and so on. And it's pretty big, actually. And of course, the cores can speak to one another as well. Also, saying the modules can speak to one another, there is that interconnect there. Obviously, that's very important because you don't want a situation where, say, Module 1 and Module 2, you don't want a situation where Module 1 knows what it's doing and Module 2 knows what it's doing, but Module 1 doesn't know what Module 2 is doing and Module 2 doesn't know what Module 1 is doing. In other words, you need that concurrent data, that you need to be able to pass that backwards and forwards. So there was always the question, quite early on, well, why go with that? For example, there was the pile driver architecture. Nick replied, the extra power and area associated with getting an additional IPC boost, instruction per clock, by the way, boost going from Jaguar to pile driver, it's not the right decision to make for a console. Being able to hit the sweet spot of power and performance per area and making it a more parallel problem, that's what it's about. How we're partitioning cores between the title and the operating system works out in that respect. So, just to clarify, all he's basically saying here is that the AMD Jaguar gave the best bang for the buck. The pile driver increased the heat too much, well, in their personal opinion, and they also felt that it was too big, the area was too large, they were putting out too much heat for the console, they just weren't happy with it, they wanted the quietest system possible. They decided as well to go wide, in other words more parallel. All that simply means is that they have more cores so they can spread the love between all of them. Obviously that simply means that they have, I believe, 6 available for the operating system, which is responsible for the game. So in other words, the games can handle 6 cores. Although there is talk about them trying to get it down to, well, up to 7. And all this basically means from the game's development perspective is that developers need to start basically programming in wide. This has actually been a fairly similar problem that a lot of people have had. The simple thing is that the higher the clock speed, the more power you require to run it at. And it's pretty much going into Moore's Law territory. If you want to know a lot more on that, you can either Google Moore's Law, and I've gone into it somewhat on the channel and explained why Moore's Law is having a few issues right now, so you can just Google Moore's Law. That's M-O-O-R-E, for those of you who are not quite familiar. Anyway, moving on. So there was asked about the Jaguar. Did they customize it? And they said there had not been a 2-cluster Jaguar configuration, we just discussed that, before the Xbox One, so there were things we had to be done in order for them to work. We wanted higher coherency between the GPU and the CPU, so that was something we needed to be done. That touched a lot on the fabric around the CPU, and then looking at how the Jaguar cores are implemented virtualization, doing some tweaks there, but nothing fundamental to the ISA or adding instructions, or adding instructions like that. So basically all they're saying is they didn't increase, they basically worked with the chatting between the CPU and the GPU to make sure they knew what the hell they were talking about. But what they didn't do was they didn't add or change or remove any of the x86/64 instructions. There's nothing special going on there. There's no like special Microsoft instructions on the CPU or whatever. Instructions are basically, well, easily access commands. Let's just go with that on the CPU. So you can write a very small bit of code which can access those instructions and tell the CPU to do something like move a piece of data in memory. This is basically known as CISC, and the x86-64 uses CISC, that's CISC, which is complex instruction set computing, versus RISC from the Power architecture. The Power architecture, of course, was prevalent in the last generation. The Wii used it, the Xbox 360 used it, the PlayStation 3 used it. It has some benefits, we've gone into this before, but you can check that out on a different video, which is basically CISC versus RISC. You can just search CISC probably on the channel, that would come up. But effectively, simply put, it has benefits, including that it gives you, for example, more CPU registers, which are very tiny pieces of memory on the CPU, not to be confused with cache, and other bits and pieces. So in other words, CPU performance is technically higher, but the problem with that is that you're sacrificing die space for those registers, for example, for the instructions, because the instructions actually take die room. In other words, they take room up on the CPU, and the problem with not having those is it can make code a little bit lengthier, because you actually need to then code those in, make your own libraries and so on. But anyway, I digress a little bit. I like to jam-pack these 30-odd minutes videos with as much information as your brain can digest, I tell you, and then I like to put in more so that your brain's like a sponge. Anyway, so one question that's been consistent, let's go with that, is the 15 processors. Microsoft has said, well, we've got 15 processors on our system, and everyone's scratching their head and like, well, I don't get where that's coming from, really. Could you explain that? Because, you know, people were adding up the CPU cores, and they were saying, well, CPU cores plus the GCNs, that's not working, and they were saying, well, audio plus, I don't get it, what's going on, where's their medicine? So Nick responded and said, on the SOC there are many parallel engines. Some are more like CPU cores or DSP cores. How we count to 15, 8 inside the audio block, 4 move engines, 1 video encode, 1 video decode, and 1 video compositor and resizer. The audio block is completely unique. That was designed by us in-house. It's based on 4 tensilica. I'm hoping I've pronounced that right. I'll read it out to you guys. I'll spell it out to you guys, shall I say? TENSILICA. DSP cores and several programmable processing engines. We break it up as 1 core running control, 2 cores running a lot of vector code for speech, 1 for general purpose DSP. We couple with a sample conversion, filtering, mixing, equalization, dynamic range, compensation, then also XMA audio block. That was a lot to say. And the goal was to run 512 simultaneous voices for game audio, as well as being able to process speech, pre-processing connect. We'll go into some of this a little bit later in the interview because it harks back to some CPU stuff that they were referring to regarding the clock speed increases, but effectively Microsoft weren't happy with the previous generation's audio. It basically works out that they feel that the previous generation audio running a lot of different effects. This is exactly the same, by the way, as what AMD are trying to do with the PC. Just a short little divergence, and I'll let you know what I'm talking about there. They're also trying to add their own DSPs, digital signal processing, because audio hasn't really moved on that much, and they were pushing a lot of stuff over to software. Now, it's great that CPUs can do that. You know, you've got the APIs and so on to do it, and you've got the CPU power to do it, but it's also very costly, particularly when you start adding in special 3D effects, reverb, for example, dynamic 3D. There's another one. So, in other words, audio positioning. A lot of that is extraordinarily expensive to do in software, and developers were finding that one of the CPU threads, or more in some cases, depending on what's in the game, would basically be nommed alive by audio. In other words, they would basically have to dedicate 1 CPU core purely to run this audio. And it wasn't really ideal, especially because the Jaguars are low power devices. They don't really have that amount of performance to give up. You don't really want to be giving away one of the cores simply to be processing audio, especially when you can create your own particular brand which will do a lot of the work for you. If you're very curious and you have a love affair of the Xbox One's audio, you can actually, you know what I'm about to say, I've done a video on this already. You could simply search DSP and you would probably, or Xbox One DSP, I'm sure either would work, and you'll probably pop up with a video regarding the Xbox One's audio block, or you could type in audio block as well and that would also pop up. And that will give you a lot of information on that, more than I can fit in on this set of videos. I apologize, I keep saying you can watch this video. It's not to get more views or anything like that. It's simply because I've talked about all this stuff before, and some of those videos that I'm telling you guys to refer to, they're like, 15-20 minutes just to explain what something is, and so this series would be so lengthy and I'd be just padding it out, so it's just better just to tell you to watch something else if you're not sure how it works, or you can Google it or whatever makes you happy. So move engines, I've also once again done a video on that, but move engines are very simple. They're not that complicated. They're basically fixed function processors. All they do is offload tasks from the CPU and the GPU in terms of moving data around. So they literally say, okay, well, I'm going to move this piece of data for you, and I'm going to move it to there, and then I'm going to move it back to there, and so on. As I said, I'm going to do this a lot more in depth, but Microsoft believe that the amount of data that's being shifted around, the purpose is that even if the CPU, the GPU are choking to death and they can't handle any more data, the engines can't take any more, Captain, type of thing, it's fine. The move engines could do their thing. It's not going to affect anything. I actually really like that, actually. I actually think it's a really good piece of engineering by Microsoft, because in theory, it will actually promote better data flow around the system. It will reduce overheads, and that's actually pretty cool. Anything that can do that, anything that could take away the work from the CPU or the GPU, in my personal opinion, is a happy fun time. Okay, so I'm going to address one last thing. There's concern that custom hardware may not be utilized by multi-platform games. Now, Nick responded, yeah, Andrew can talk about the middleware point, but some of those things are just reserved for the system to do, like things like Connect processing. These are system services we provide. Part of the processing is dedicated to the Connect. Andrew responded, so a lot of what we've designed for the system and the system's reservation is to offload a lot of the work from the titler on to the system. You have to keep in mind that this is doing a bunch of work that is actually on behalf of the title. We're taking the voice recognition mode in our system reservation, whereas other platforms have that code that developers have to link in and pay out of their budget. Same thing with Connect, and most of our NUI, or Natural User Interface features, are provided free for the games, and also the game DVR. I'm just going to clarify what the heck he means there. All he basically is referring to is that they're saying that their title, such as voice recognition, the DVI, most of that stuff, the games don't need to worry about it. In other words, it's not coming out of the game's memory, it's not coming out of the game's GPU, it's not coming out of the game's CPU time, and all that's going to happen is that the system itself is going to handle that. So the system has the allocated resources, the system will give up some of those resources, whatever they are, and it will then be able to utilize those resources to run whatever services are required without interfering with the game. More to the point, the game's developers don't need to think, okay, well, let's just make up a couple of figures. Let's say it has 5 gigs of RAM. I'm just making this up on the spot. Let's say it has 5 gigs of RAM, and we want to do X, Y, and Z as well, which is system orientated. Well, they don't need to worry. They've got that 5 gigs of RAM to do the game's code, and all they need to do is tell the system to use that. Things as well, I'm just going to throw this in here as a bonus to you guys. Things such as the move engines don't, as far as I'm aware, because of fixed function accelerators, they don't really require much code from the developers. They're basically there just doing their thing, chilling, hanging out, just doing their thing without instruction, really. So there's not too much in regarding the developers have to do there. But that's about it for this video. Now, I would keep going, but whenever I go over like the 35-40 minute mark, I get comments saying this video is too long, and so I try to keep it at 30 minutes. Hopefully you've enjoyed the video, however. I will, of course, get right back on this, so see you soon. Take care, and bye for now.